All right, welcome to class. Let's get going on this new probability lesson. You should have set up your page for Cornell Notes. Your warm-up should have already been done, and probably you're in the habit of writing down the objective, but in case you forgot to do that, make sure you've written that down. So the title of today's probability lesson is Dependent Events. And I guess to get our lesson started, let's kind of talk about independent events. There's a good chance recently in our class we did the coin flipping activity. I think just about all the classes did that. And we kind of saw that each flip of the coin was what we call independent. In other words, just because you flip the coin and get tails, that has no bearing on what's going to happen the next time you flip the coin. They are completely unique and have no connection to each other. Today we're going to work on some problems where what happens one time does have an effect on what happens the next time. Most of the time this will affect our sample space, usually making it smaller. So anyway, let's go ahead and dive into this. Have your pencil ready. Here comes the first part of our notes. So let's write down dependent events, and here's some facts you need to know to do these problems successfully. Okay, so here's a definition that you should write down for what a dependent event is. Or dependent events are two events where the outcome of the first event has an effect on the probability of the second event. In other words, instead of being entirely separated from each other, these are connected. So what you get the first time matters because it has different effects on how you do the probability for what happens next. And I think if you think about real life, this happens quite a bit. So here's kind of some real life examples of how one thing can have an effect on the next thing. So here's maybe a very probability problem kind of example. Let's say I shuffle up the cards and I spread them all out and I let you pick a card and you pick one, but you don't give it back to me, and I go to another student and say, okay, now you pick a card. Would that affect the probability of what they could pick since you kept your card? So we'll probably even do that problem today in the examples. Here's another one, and you should be copying all of these down. Okay. I think all of us at one time or another were involved in picking teams for sports or some sort of other competition. Even when we play the game in class, this kind of takes place. So let's say you're all standing there and there's two captains picking teams for a, I don't know, dodgeball game. And the first person picks and that person's on their team, and then it's your turn to pick. Didn't whoever they pick kind of narrow down who your choices might be? So if you were randomly picking, right, your sample space for making your choice got a lot smaller. And if you pick somebody, in fact, by the end, when the last person's picked, maybe that's happened to some of us in here, right? The person doesn't have any choice. The sample space has gotten down all the way to one person, and they kind of pick you, but you're just it. So, okay, I'll take you. Okay, and the big idea here with dependent events is that there's going to be a different sample space because maybe some of the possible choices have been taken away. And of course, if you change the sample space, that will affect the probability because we need the sample space to work out our probabilities. All right. Last thing we need to put down in your notes is that we have been studying we learned there was an OR formula. There's a formula for working out probability that involves AND. There's even a formula when you need to find the expected number of results. We've learned that one more recently. So what about today? Is there some dependent events formula? And as you can see, as you're writing in your notes, there is no formula for doing dependent events. You just kind of think through the problem and do a normal probability event over sample space. But you just kind of have to think it out all right, what's left if something has been affected? All right, let's try our first problem. Take a moment and copy this one into your math notebook. And once I've given you enough time to write it all down, we'll see if we can work our way through it. It says that a spade is drawn from a deck of cards and not replaced. In fact, I would say if there's like some keywords, and hopefully you notice I put it in blue right now. Okay, probably some of the keywords that tell you, hey, be careful about your sample space because there's a dependent event going on, is to see stuff like not replaced, or maybe somebody's eating a bag of candy and they take an M&M and eat it. That's supposed to remind you, like, well, we kind of hope that one's not going back in the bag if they've already eaten it. Okay, so you need to kind of keep your eye out for words that are trying to remind you, hey, something just happened and it's not like going to go back to the way it was before. So we have a dependent event. So a spade is drawn from a deck of cards and not replaced. Find the probability that the next card drawn is a spade. So let's see. Let's see how we would work this one out. So let's do some notation. What are we trying to find the probability of? The probability of drawing a spade. Now, not from just any deck of cards, but from this particular deck of cards. So here we go. That's going to be, let's do the sample space. So normally we wouldn't even have to almost think about this, right? How many cards in a deck of cards? There's 52. But is there 52 this time? Well, if a spade was drawn from the deck of cards and not replaced, how many cards are there? Well, that one is gone. That means we're left with 51. And like we mentioned earlier, you just kind of have to think this out and like do any math that's needed in your head. All right, now we need to figure out what's the event of getting a spade, and most of the time we would jump right into this and just say, well, there's 13 spades. But are there 13 spades sitting there when we go to make our choice? Well, what did they tell us? That a spade was drawn from the deck of cards first. So are there 13 there? There are not. That one spade was not put back, so there aren't 13 to pick from. How many are there to pick from? There are 12 spades to pick from, and that right there would be the probability of randomly choosing another spade from the deck of cards that's left after we took that one out. Okay, let's try a different problem. We're going to do 3 today. I'll do 2 with you to help you kind of get the feel for how these dependent events work. And then we'll give you a problem to see if you can get correct on your own. Okay, here's our next problem, and just like the first one, you should take a moment and copy this one down. Okay, it says there are 2 yellow marbles, 1 green marble, and 3 red marbles in a bag. Okay, so we got this bag of marbles. They're different colors. They're all in there mixed up. We're going to reach into the bag and randomly pull one out. Because they're in the bag, we can't like pick the one we want. We're just going to see what are the chances that we get the one we want. And here's the question. Find the probability of choosing 2 yellow marbles, and then there's our keyword, without replacement. So while you're copying this down, let me get this out of here. Without replacement. So what do they mean by that? Well, we're going to reach into the bag and pick a marble, and we're not going to put it back. So we're going to take it out, put the marble down, and reach back into the bag for a second marble. And because we didn't put that first marble back, is that going to affect the sample space and the probability of what we get on our next reach into the bag? Of course it will. What was there isn't there now. All right. One other thing I want to point out to you is that they say find the probability of what? Choosing 2 yellow marbles, like one after another. And this is one of those tricky problems where it is actually, we want what? Both of these to be yellow? Both maybe will help us see that this is really an and problem. Except they're being really sneaky. Did they say and? They didn't. But we want to reach in, grab a yellow, take it out, and reach in and grab another yellow. So this is an and problem. So we're going to find, let's see, how would we work this one out? We need to do the probability for reaching in and grabbing our first yellow. And then we'll do the probability of reaching in and getting the second yellow. And because it's and, what does that tell me I need to do right there to get the probability that both of those things will happen? It's hard enough just to get one. To work out the probability that this will happen both times, we're going to multiply. This is going to make the chance of both of these things happening go down. Okay, let's do some probabilities. So how about the sample space on our first reach into the bag? Well, there's 2 yellow marbles, 1 green marble, and 3 red marbles. It looks to me like that's 6 total marbles that we're going to be picking from. And on our first reach into the bag, what are the chances that we'll get a yellow one? Well, how many of the 6 marbles are yellow? There are 2 of them. All right, so we got our first probability done. But we want to choose 2 yellow marbles, one after the other, and we're not going to replace. So this is why this is an AND problem. All right, so we made our first choice, and we're going to reach back into the bag, but we didn't put that first marble back. So what's the sample space now? Inside the bag, waiting for our hand to scoop one out, there's how many marbles there? There are 5 marbles left because we took one. All right. And we are trying to get the probability that both of them are going to be yellow. So we're going to assume that the one we got the first time was yellow. So if we're reaching in again, what are the chances that there will be a yellow marble in there? How many are still in there? Well, if we're assuming we got a yellow marble on our first draw, how many will be left? Just 1 marble, right? We had 2 yellows to start with. We took one out, hopefully. And what are the chances that the second we pull out? All right, so now it's just a simple multiplication problem. So 2 times 1 would give us a 2, and 6 times 5 would give us 30. There is a 2 in 30 chance, or maybe we could say 1 in 15 chance that that would actually happen, that you could pull out each yellow marble one at a time. Okay, ready to try one of these problems by yourself? Okay, so here's our last problem of the day right up here. Please copy it into your math notebook. Once you have it copied down, see if you can work it out, and you should expect there to be some sort of dependent event. So here's what it says. Someone grabs a deck of cards and flips them over so they can see them all, and removes five diamonds. Gone. Takes out the 5 diamonds and burns them. I'm just kidding. They just take them out. They want you to calculate the probability that the next randomly drawn card is a club. After you take the 5 out, then you shuffle them all up. You turn them over so nobody can tell what's what. You let someone randomly pick any of them. What are the chances, what's the probability that that randomly drawn card is a club? All right, what I'd like the substitute teacher to do is pause the video to give all of you enough time to work this one out. Once most of the students have this worked out, you can unpause the video and you can check and see if you worked this one out correctly. So pause the video now. All right, so here's what you should have done. So we're going to do the probability of drawing a club. And what's our sample space? Well, normally, without even thinking, we could just blurt out 52. But what's going on? They removed 5 diamonds. So are there 52 cards there? Nope. How many cards are there? There are 47 cards. We don't have a full deck. 5 diamonds are gone. Now they want us to calculate the probability that the next card we draw is going to be a club. So what should I fill in here? Well, normally we would fill in 13. Do you still fill in 13? Actually, how many clubs are there? Are all 13? Yeah. All the cards they took out before, they kind of purposely chose diamonds. So all 13 clubs are there, and that right there would be your answer. And you could turn that into a decimal or a percentage if you wanted to, but that's really not necessary. There's 13 out of 47, and that would be your probability. Okay, up next, our substitute teacher will pass out some practice problems. It's one thing to hear the teacher talk about how to do this. It's a whole other thing to get enough practice that you are good at this. So that's what today's assignment will do for you. The assignment you'll work on until the end of class. I think I'll have you work individually. You can ask each other for help and compare answers, but stay in your regular assigned seats. And what you don't finish will turn into homework due the next time we have class. And the teacher will pass out the paper, and you can go ahead and get started.